My program, I have an extensive program on photovoltaics, and there are two aspects to photovoltaic technology that we're pioneering in my laboratory. One is the use of what I call the inorganic side. One is the use of novel carbon nanomaterials to make new kinds of photovoltaics, really enhance the photovoltaics that we already have. So in one area, we're taking carbon nanomaterials like single-walled carbon nanotubes or graphene. We're making photovoltaics that can be stacked in tandem with a silicon photovoltaic cell. So one thing that we've done in my lab is we've made, for the first time, an all-carbon photovoltaic cell. It happens to be a near-infrared cell. So it's especially good at taking near-infrared light and converting that to electrical energy. And the reason why that's important is because if you look at the solar spectrum, about 40% of the energy in the solar spectrum is in this near-infrared range. So this is light that's so red that your eye can't see it. Conventional photovoltaics, because they're based on a band gap, say a silicon photovoltaic, it doesn't harvest this light for electrical generation. That light just goes into heating the device and lowering the efficiency. So the idea here is to take a near-infrared photovoltaic and stack it with a conventional, say silicon photovoltaic or other material, so that as the sunlight passes through the device, each of these active layers will harvest an increasing portion of the spectrum. And so what we're hoping is that this will increase the overall efficiency of the light capture, and also help to control the temperature of conventional photovoltaic cells, because as they heat up, their efficiency drops. By capturing that 40% of the solar spectrum that's missed in many of the technologies that are out there today, we hope to increase the efficiency of light collection. So as you increase the efficiency of solar energy conversion, more and more applications open up. You can also lower the cost of such devices, and you can harvest more energy from a smaller footprint device. We've also designed these interesting Exoton antennas. This is an idea where we could make nanostructured elements that have the ability to take photons and collect them almost like a funnel. So imagine I could take a photovoltaic device and I could put on antenna structures that can absorb and collect photons from an area that's much larger than the device itself. Think of a funnel. Suppose I made a funnel for photons, just like you have a funnel for rain droplets. You put the funnel in the rain, and you're able to collect and concentrate water that's falling from the sky into a small spot. This gives engineers a new set of tools that they can use to design light harvesting technologies, besides just a flat panel that has to be pointed towards the sun. Imagine instead that you had a fabric, or you had a surface that had embedded high efficiency photovoltaic devices all throughout its surface, and you had these antennas funneling and collecting photons and putting them into the device. What that means is that, say, instead of having a brittle silicon photovoltaic, you can now have a flexible, perhaps a rubber surface, perhaps a garment, so it gives engineers new tools to collect light in interesting ways.